Hello, everyone. We're starting the next session, last day of the conference. This session is called General Video Game AI Playing. I am Gabriela Barros and I'm chairing it. Let's all welcome the first speaker. The paper is called Rolling Horizon Evolution Enhancements in General Video Game Playing. And the speaker is Raluca Gainer.
Close enough. Hello, and thank you for the introduction. My name is Raluca Gainer, and I am an IGI student from the University of Essex. And today we'll be talking about some experiments we did playing around with Rolling Horizon evolutionary algorithms in general video game playing, and some modifications we tried to boost the performance of this algorithm. This domain has been dominated for a long time by Monte Carlo tree search, but in the context of the general video game AI competition, it has been shown that the Rolling Horizon evolution does show some promise of matching and even surpassing the performance of MZTS. We have two other papers that are published in similar areas of Rolling Horizon. I should not touch cables. If you want to learn more, there will be a link at the end for my website where you can check it out. But in this particular study, we focused on some modifications in previous literature that have been explored in various contexts and in various parameter settings. So we wanted to bring them in general video game playing and also give them a consistent environment to test them, see if they work and if they work well together as well. When we are talking about game playing AI, it's usually one agent that is able to play a particular game, like Go. A lot of people just immediately go to that these days. But there are also a lot of researchers taking interest in StarCraft, and the AI is getting better and better in these games. But these agents do incorporate a lot of domain knowledge, and they spend a lot of time training on these particular games. And if you took them and asked them to play a car racing game, for example, they would just probably crash the car the first chance they got. So what would be more interesting and what our group is focusing on is general video game playing. So getting one agent that is able to play several games and even unseen games that it's never seen before, it's never been trained on, but it is able to adapt to these new scenarios. And this can, of course, have some applications in the game industry and even the real world, with removing the need to come up with new tools for every project you're starting. You can just get some general ones. Or for game testing, currently you'd have to employ several testers to see if the game you created works in the way you intended, and if it's easy or hard. So instead, you could take one or a bunch of these general agents with different behaviors and analyze how they do, and at a much lower cost. And to that extent, we are working in the general video game AI competition, which has been previously covered briefly, so I will not go into much detail, but we are focused on the single-player planning track, and in particular the 2D grid physics games, which there are about 100 in the framework at the moment. And these games vary in many ways, from the options for the player to interact with the environment to the scoring systems in the games and what makes games end. But all they actually get to know about the games is a very high-level overview of the current game state. They only get to know that there's an object in this game. They don't know what it does, what happens if I go and interact with him, so they have to figure this out, and they have only 40 milliseconds of thinking time to actually make decisions. In this domain, we apply the Rolling Horizon evolutionary algorithm, and I will try to highlight the parts of this algorithm that we addressed in this study as I go and explain it. So it first starts with a population of individuals that is randomly initialized at every game tick, and this first step is actually the first part that we addressed, which we called population management. These individuals battle it out in a tournament, and two of them are selected for crossover, where each individual represents a sequence of actions to be executed in the game. Then we apply a uniform crossover in the vanilla version of the algorithm. So we're selecting random genes from each of the individual and combining them to form a new one. And then we are mutating this individual by selecting one random action and replacing it with a new random action. This is the second part that we are addressing in this study, the mutation operator. Then we have to evaluate this individual to see if the sequence of actions that we obtained is actually any good or not. So in order to evaluate it, we take the actions in turn, we put them through a form model that simulates the game state that we would get to if you were to apply this action in the actual game. And once we get to the end of the sequence, we evaluate the final state through a heuristic that gives us a value representing how good the sequence of actions actually is, and that becomes the fitness of the individual. This evaluation part is the third that we will be addressing, the individual evaluation. And finally, the process is repeated for all the individuals in the population, except for the first one that is promoted directly through elitism. And at the end of all the generations simulated, we will select the first action of the best individual to actually play in the game. And that is the last part that we are concerned with, and that is the action recommendation policy. And for a brief overview, so we'll be looking at mutation operators, population management, action recommendation policy, and individual evaluation. We'll be looking at this in isolation as well as combined to see if they form some interesting things together. But because there are so many combinations between them, and we also looked at different parameter configurations, we split this into two parts, where we looked at the first three first, and then we added the individual evaluation to the best algorithms in the first part of the experiment. We tested each algorithm on 20 of the games in the GVGA framework, and with different core parameter configurations. So the first enhancement that we looked at is the mutation operator. And for this, we replaced the random mutation that we had before with a UCB-based mutation that we called EA bandit. And for this, we have two layers of bandits. First at individual level, which selects which gene to mutate next. And then we have lower level bandits for each particular gene that decides which action should be chosen. And for this, we use the UCB equation that basically balances between exploitation of good actions and exploration of possibly good actions. Then we have population management. For this, we looked at a shift buffer, and we call this EA shift. The idea is to retain information between game ticks. So we spend all of this limited time that we already have, and we go through a whole process of evolution. And in the vanilla version, we would throw all of this away and start fresh with a new sequence of actions from the next game tick. But with this one, we choose to remove the first actions of all the individuals in the population and just add a new random one at the end. So we're still keeping that information and try to evolve on top of it. Then we have the action recommendation policy. This is keeping a statistical tree alongside the evolution. We call this EA tree. And the idea is that when you evaluate an individual, you keep all of the actions that you go through in a tree. And over time, you accumulate that information. You get to understand more about how useful an action actually is. And at the end of the evolutionary process, we use this statistical tree to recommend the action as the most visited at the top level of the tree. This is different to Monte Carlo tree search because the statistical tree is only used for statistics. It's not used to guide the search in any way. So we only use it at the end to see which action is actually better. And finally, we have the individual evaluation. Normally, we would go through the sequence of actions, and that game state that we finally reach would be evaluated to see what happened. But in this version, that Vanessa might know some more about as well, we apply some random rollouts at the end of the sequence of individuals, and this would increase our search horizon a bit, but in a more dynamic way. So we don't have a specific set of actions that we will go through. We are randomly sampling and trying to increase that look ahead. And the length of the simulations we chose in this experiment was half of the length of the individual. For the actual experiment, we tested 4 different configurations for each of the algorithms to see how the population size and the individual length actually impact these specific enhancements. All the other parameters are fixed to some default values, which I won't go into detail about. The budget was set to 900 calls of the 4 model, so 900 simulations of what happens next in the game. We chose to do this instead of the 40 milliseconds in the competition because it would be machine independent, so we wouldn't have to worry about fluctuations on the machine we ran the experiments on. And 900 is the average that the vanilla version of the algorithm achieves in the 40 milliseconds in the actual competition. So in the first part of the experiments, we looked at the first 3, the EA Bandit, EA Tree, and EA Shift, plus all of their hybrids and their combinations together. In the second part of the experiment, some spoilers, don't mind those, we took the best algorithms from the first part, which turned out to be EA Tree and EA Shift, and we added to those EA Roll. And finally, we validated against MCTS to see if this is actually any good, and we are achieving our purpose of beating this algorithm. For the games that we selected, we chose 2 classifications in the literature that rank the games depending on the performance of Monte Carlo tree search or various other agents in the competition. And we randomly sampled from this, which would give us a nice distribution of game difficulty in our game set. And we ended up with 10 stochastic and 10 deterministic games of varying difficulty and game type. And these are just 4 of the games that we ended up with. Aliens has been briefly described before, and you might recognize Missile Command as well as a classic game. For results, the shift buffer enhancement, so the one that preserves information between game ticks, turned out to be the best one, while the bandit mutation was the worst. We actually observed a performance proportional to the parameter values that we've seen before in our studies. This was not very surprising, but one thing that was interesting was that the shift buffer enhancement manages to perform a lot better than the best vanilla algorithm in its low configurations. And the low configurations means that you get to do more generations, more evolution. So with this algorithm already being a lot better than the vanilla version, it means that there's a lot of space to improve the evolutionary process and get even better performance. And we have here a heat map which shows the number of significant games in which the row algorithm was better than the column. So the darker the color, the more games there are. And the way to read this is basically looking at the rows for the best algorithms and the columns for the worst algorithms. The darker the column, the worse the algorithm. And we can observe that algorithms A and B, which are vanilla and EA shift, stand out as the best rows. And for the columns, we also notice that F and H, which are EA bandit shift and EA bandit tree shift, they stand out as the worst. And to go quickly through each of them in particular, we have first EA Bandit, which turned out to be the worst variant. And this was mostly because our individuals in the population are sequences of actions. And due to this, when you change one action in the individual, the rest of the actions change their meaning. So for example, if you have an up and then following a path through the level, if you change that up to a down and you follow the same path through the level, you would end up in a different place. So that is one of the issues with this system. Our bandit system only looked at genes as individuals and not as the sequence of actions that we were interested in. So that would be an interesting thing to improve. then the EA tree turned out to be the best in the lower configurations. And that is mostly because with more time to do more generations with the lower configurations, then we would get more information to add to our tree, and the information become more accurate about what's actually good in the game. So that does make sense. And our EA shift turned out to be the best variant, with achieving higher scores in most of the games, significantly higher. And its worst hybrids were with the bandit mutation. For the second part of our experiments, we looked at adding these simulations at the end of the individuals. And the best algorithm turned out to be the EA shift role, which is combining the information retention between game ticks with the rollouts at the end of the individuals. The rollouts turn out to be the most advantageous in low configurations, which means that given that we are already offering some part of our limited budget to these rollouts to perform some more look ahead, it does make sense that we can do more in lower configurations, so we get more information and more benefit out of them. All of the variants turned out to be better with rollouts than without them, except for the tree search. It turned out to actually be worse to keep the statistical tree next to these rollouts. And finally, we performed a validation against Monte Carlo tree search. We looked at the best algorithm and the one that is most similar to MCTS out of our selection. So the best algorithm achieves for the first time something that we've been looking for, and that is to match the generality of Monte Carlo tree search. In our previous work, we have obtained better performance than MCTS, but that would be in a specific set of games. The performance would only increase there. In this work, we have managed to match the generality, which is measured in the GVGAI competition by Formula 1 points, which is basically a way to normalize the scores. So an agent that scores very well in one game and very poorly in all the others should not be better than another agent that achieves an average performance in most of the games. And then we looked at the algorithm most similar to MCTS, which is EA tree roll, the one that keeps the statistical tree as well as doing the simulations at the end of the individuals. And this turned out to actually be significantly worse than MCTS, but it still is better in puzzle games. So to conclude, our bandit system did not work because of this idea that sequences of actions have a different meaning that the system was not able to handle. The statistical tree turned out to be most beneficial in lower configurations, while the shift buffer increased the scores that the agents were able to achieve in the games quite significantly. Then we also saw that the shift buffer with the rollout enhancements saw an increase in performance inversely proportional to the individual length. So the more rollouts we could do, the better. And our best algorithm was the EA shift roll with a configuration of population size 10, individual length 14, and 5 repetitions of the simulations, which manages to match the MCTS generality. And for future work, we will be looking at meta-heuristics, so a way to dynamically adapt these algorithms and decide which one we actually want to use at the problem at hand. Because even though we did get an algorithm that seems to be more general and get a good performance, there are some that perform better in certain scenarios. So it would be great to switch to those in specific situations. We might look into bandit mutation and improve that to actually handle the idea of sequences of actions and not just look at them individually. And we would also like to explore more games to better judge significance. We do have 100 of them to look at, and the number is growing. Thank you.
So now we open for questions. Please come here if you have any questions.
Oh, no, there's a queue.
So you said that you used uniform crossover in the vanilla version. Yeah. Did the other versions also use vanilla crossover or crossover at all? I was unclear on that.
Crossover was uniform in all of the variants, yes.
So I think that that could also be introducing a problem because of the same issue with the bandit. Because if you arbitrarily mix actions, then you destroy the action sequence. Yeah. And so if you did a single point crossover, then anything that's beneficial on the left side would be retained, and you'd only be varying what happens after that. So I mean, just exploring different kinds of crossover, I think also would be a way of improving this.
Yeah, that's a very good idea, and we'll definitely look into that. This was mainly exploring things that have been done previously in literature, so we played around with those, but it's definitely a very good point.
There are a lot of unusual forms of crossover that are maybe less well known, but there's tons of variants, and I think that there are some that are specifically designed for sequences of actions. And so if you search deep enough, you should be able to find them.
Yeah, thank you. Yeah. I'll definitely look into that.
Hi. That's a cool animation, by the way.
Thank you.
Very distracting as well. So I think it was a really good idea to try to have a set of games that are as diverse as possible, right, by doing this characterization stuff. But I was wondering how many of the games were actually, like how many of the games where the agents were actually able to play something, like where there's meaningful, because you in the VGA competition you got lots of games where either all of them win or none of them do anything.
That was definitely one thing that we did take into account when we selected the games. So we did try to look at games where something actually happened and they did manage to win sometimes or get some kind of score. But there are a couple of games that we thought we should include at the bottom of this ranking because maybe some kind of enhancement combination would perform actually and manage to break out of this non-win scenario. But that is a minority of our game sets. In most of the games, they actually did stuff.
So that worked?
Yeah.
Were there some games that were...
There were some games that did go from 0 to something. That's not much, cool. But something.
Right, thanks.
So that was cool. Thank you.
Thank you.
I was thinking about the shift variant, and it did really well. You tested it, and it's because it's saving a lot of work that you've already done evolving, right? Yep. So if the population is evolving towards something that's a good solution to the game, absolutely. Are there games where there are strategic local optima and using the shift variant could drop you into a local optima and get you stuck?
That is possible. And one of the things that we did try with this shift buffer as well was to introduce some information loss. So we would try to forget about things that we've learned after a certain time so that we do try to avoid this and introduce new things into the population, get out of that.
Okay, you're already on top of it.
Yeah, thank you.
So it's cool work, and I'm happy to see that this really works. And yes. With Ivan Bravi, we tried something a little bit similar. Also the shift thing, it didn't get it to work. We never submitted it. We sort of went into a different direction after that.
Okay.
But so I wonder about the bandit mutation. It seems that it didn't quite work, and I understand that mutating sequences is action sequence is a tricky thing. What was the reasoning behind it? Why would it work?
The UCB one?
Yeah, the bandit-based mutation.
It was mainly based on work that Jolene and Simon have done before that used this bandit mutation in a random mutation hill climber. That is slightly different to what they did, but we did think, hey, why not try it out to see if it actually works?
But the bandit would reset for every new run of the evolution?
Yes.
Or for every generation even?
It wouldn't be for every generation.
No, but for every generation.
Yes.
Is it maybe just that 900 function evaluation is too little for it to work?
That is very possible, yes. We've not tried it. So.
I think just to clarify with the bandit. So the version of the bandit that we used in this paper was an old version of the bandit, so it wasn't the entable bandit. And regarding the small number of evaluations, that's one of the reasons to use a bandit approach to get the sort of maximum benefit of what you're sampling. And I think one of the next things we need to try is with the full entable bandit that we haven't tried yet, which does take the epistasis into account. And then the other thing about that is that we need a proper shifting bandit that works with a shift buffer.
Yeah, definitely.
So I think with those enhancements, I expect it to work, and we'll have to wait and see.
Yeah.
But shifty bandit, yeah.
Okay, let's thank our speaker one more time.
Thank you.
And our next